Welcome to homework.
Okay, so we've got sodium acetate on the left. And hydrocyanic acid on the left. And that's in some sort of equilibrium. We don't know which side it favors, with acetic acid and sodium cyanide. We're asked to determine which side of this reaction is favored, and I believe the best way to go about this is to determine what the pKa of the acid forms of the two molecules are. So this is the acid form of hydrocyanic acid, or hydrogen cyanide. This is the base form, the conjugate base, right? This is the acid form of acetic acid, and this is the conjugate base, right? And when we've got things as we have, like going from left to right, typically we refer to the pKa of whatever's in an acid form here as the pKa, and we'll just kind of Google this. This might also be in your textbook, but the pKa of hydrogen cyanide is about 9. And the pKa, or what we call the pKaH, so we say, okay, this is the conjugate base on the left-hand side, and we refer to the acid form of whatever the conjugate base on the left-hand side is, which would be on the right-hand side, is the pKaH, right? So it's like saying, we've got, on the left, we've got acid, and we want to know the pKa of that acid. And we've got base, conjugate base. And what we want to know is what's the pKa of the protonated form of that base. If we take this base and add a proton, what's the pKa? So this pKaH is actually the pKa of that acid, right? And that's about 5. Okay, so now we've got the pKaH of the conjugate base and the pKa of the acid, and what we can do with this is determine what the equilibrium constant would actually be. We can actually mathematically calculate the equilibrium constant, and whether it's greater than 1 or less than 1 will tell us what side of the reaction is favored. Okay, and the way we do that is we do K is equal to 10 raised to the power of the pKa H minus the pKa. Okay, so we're talking about what is the pKa of the acid form of the conjugate base on the left. That's what goes here. And then we're saying what's the pKa of whatever the acid is on the left. That goes here. So this is going to be 10 raised to the 5 minus 9, or 10 to the negative 4, right? Which is much less than 1, right? If k is greater than 1, then the equilibrium arrow points to the right. If k is less than 1, then the equilibrium points to the left, right? So just by doing that, we know that the side that's going to be favored is the left-hand side. Right? That's how you do it mathematically. Without math, the only way to do it is to determine what's the stronger of the two, right? So maybe we don't know what the pKaH or the pKa's are, but we're still interested in the pKa and the pKaH, right? We may not know the numbers, but we still have an idea, okay? And what we do is we look at the conjugate base on the left, and we say, is the pKaH of that conjugate base, meaning the pKa of the protonated form of that conjugated base, the acid form, stronger or weaker than the pKa of the acid we have, right? So in our case, we would just have to know this. There's no way to know it a priori, but hopefully you'd have a table or something you could look it up and you know, okay, this is the strong one and this is the weak one. Okay. That's what we determined when this one had the lower pKa, right? 5 is lower than 9. The lower the pKa, the stronger the acid. So the pKaH, right, the acidity of this molecule is stronger of an acid than this molecule. Okay, that's what we're talking about. And what we're going to say is that the reaction is going to favor the left if the pKaH is stronger. If the pKaH is lower than the pKa, it favors the left. And if the pKaH is stronger than the pKa, it favors the right. Why might that be? Well, consider that if an acid is strong, it's more likely to give up its proton. And we're more likely to dwell on the side of the equation where the stronger acid has given up its proton, right? We know that the HCN, the hydrogen cyanide, is the weaker of the two acids. If we compare these, this one's weaker. So it's more likely that this one, being the weaker acid, should retain its proton. It makes more sense to be on the left-hand side of the equation where the weaker acid still has its proton and the stronger acid has given up its proton, because that's what being a strong acid means. You give up your proton more readily than other acids. Those are the two ways you can kind of work through this problem.